Okay. Hi everybody, welcome to another episode of image enhancement. Today we'll be talking about spatial filtering. In the last class we stopped with image enhancement, especially with the intensity enhancement, where we try to stretch contrasts of an image so that it's visually better. But today we're going to see a different version of those image enhancement. This is called spatial filtering. I hope all of you've got your notes ready. For the ones that do not have the internet, you can see it anytime that you want. And for the ones that want to make your own notes and study on your own, the syllabus I've already sent it to you. So for the ones who are there and who are watching the video, I hope you've watched the previous videos, because without those videos you will not be able to really get into what I'm saying in this current video. So just to recapitulate, we've talked about why we need to enhance images. Image enhancement is one of the activities that we perform in image processing. जब हामीले image processing गर्छ त्यति बेला image enhancement is one of the activities, and after that we've got image segmentations, we've got image compressions, then we'd see classifications. So all of those things are there, but the enhancement is such an important subject, because without enhancement not much of the research work that goes on today would be possible. Especially why enhancement is important is for the fact that thanks to the internet, the Facebook, the Instagram, the Twitters, so many terabytes of images are being produced every day. Now it becomes very, very important that enhancement techniques are developed. Images are better suited to our needs. We can find certain patterns that we're looking for. So without wasting much time, the previous sections we've seen was where we did processing on images based on point processing. So if there was a pixel, input pixel, we process that input pixel to get an output pixel. So now we're coming to neighborhood processing. So in order to process a pixel, we need to compute the neighborhood of those pixels, and we're going to take a certain area around that pixel, and say we're computing a pixel x. Suppose we're computing pixel x. Now to get the desired enhanced value of the input x, we will take into consideration the neighborhood of x. Now what is the neighborhood going to be like? That depends on the mask that we're going to apply. Now this, when we take an input image and we take a neighborhood, this neighborhood is called a mask or a filter, as it says here. Okay, so we take an image, and I will go straight away to that image. Here you go. This is a perfect image. Here you go. So if this is a section of our image, and we are going to process this pixel f of xy, this is the central point. Now in order to get an output pixel g of xy at this point, this is an input pixel. I'm going to enhance this image. So just now we're going to enhance this particular point pixel. To get an enhanced value of this input pixel, central pixel, we're going to take into account a neighborhood. So that neighborhood कतिवटा पिक्सल ले गर्दा चाहिँ यसको भ्यालु निक्लिन्छ, यसको भ्यालु निकाल्नु कतिवटा पिक्सलको हात हुन्छ. So that is determined by something called a mask. This mask is also called a filter. Now these filters are of different kinds. Here we can see it is 3 by 3. So when we take this mask, if you enlarge it, it looks something like this. This -1, these are the coordinates, so the and W means the weights. So each of these pixels in the mask will have certain weights. It's also called coefficients. Now these coefficients lie as a 3 to 3 matrix. Now it so happens that this particular weight at 0, 0 of the mask always lies on the pixel that we are processing, this f of xy. So if you take this mask and put it on top of this image this W00 will always lie on f of xy, because this is the pixel we're trying to find based on all of these values. Now, who decided this area? This mask decided this area. Now, when you consider this as a signal, since image is a two-dimensional signal, so this is a signal and this is a signal. So when you take two signals and you somehow join them up and a new signal is formed, this process is in a very general term is called convolution. Now, this convolution has its basis in mathematics. It has its basis in signal processing, where two signals are convoluted when two signals are added to get a new signal. So when you have such merger of two signals to produce a new signal, especially in the two-dimensional domain of this image, then it is called spatial convolution. So what is convolution? Convolution is actually a mathematical term where two signals are combined to get a third signal. Now, since we're talking about an image and it's a two-dimensional plane, we call spatial convolution because it's a two-dimensional plane. So we are getting a new image, okay, or we're taking an input image and we're convoluting it with a mask in order to get a new image. Now, every time we're calculating, every time in spatial filtering, so here, this is what it's saying. This is an equation where we are signifying the process of convolution, spatial convolution, by this operator. So W means the mask, f of xy is the input image. So these input images, this input image with the weights of the masks, which we call the coefficients, are being convoluted, or these two signals are being added in such a way that you get an enhanced image g of xy. So this is a very general term for spatial filtering. Now, how does this spatial filtering work? So what did we see till now? We saw that in order to enhance an image, there is another process called spatial filtering. Spatial filtering makes use of neighborhood processing. So spatial filtering always has a filter or a mask. It is a neighborhood. That neighborhood has certain coefficients. Now, this neighborhood coefficients is convoluted or is added with the original image to get an enhanced output image, as shown in this equation. Now, how does it work? This mask is the one that is processing the input image. So this is the mask that we call a filter. This is the mask that defines the region. So now, if this is a section of the input image, and if you want to process this pixel, this one, the f of x minus 1, y minus 1, this is the coordinate, x minus 1, y minus 1, then you come to one right side, y remains, this is x, this is y, this is x. Okay, so what happened? This is ulta. Okay, anyways, so whenever you take this mask and you want to start processing this first pixel, this mask will overlap this pixel where such that the central pixel of the mask, this W00, this W00 must be on top of this pixel. And so all of this line of the mask will fall on this line of this image pixel, and suddenly you get a blank pixel here. So there are methods of applying additional pixels here. You can either have 0, 0, 0, or you can have the same values added on to the side of the pixel. But that's another topic again. So the point that we're trying to make is this mask will travel from pixel to pixel, calculating the values of this input pixel based on this neighborhood of the mask. Now, every time a certain pixel needs to be calculated, this pixel should fall as the center of the mask. Once this pixel calculation is finished, then the mask moves one to the right, and this center falls again to this pixel. Now, if this falls in the edge, as shown here, since as it falls in the boundary, then padding, there are techniques for padding. So that's we're not going to touch that. But for us, we can just assume that we're going to add additional zeros, and then we're going to do the same processing. So that is the way a spatial filtering works. There is a filter. Filter has coefficients. That coefficients are responsible for calculating the response of this filter. That's what we say. So the response of this filter will decide what the value of the input pixel will be enhanced to. So, and then once you finished enhancing the first input pixel, then the mask is moved to the next pixel. So this mask moves from pixel to pixel, and depending upon the response of this filter, the output image G of XY is produced. And this process is basically comparable to what we term as convolution. Now you can see this, the size of the image is 3 into 3. This is the smallest mask available. You can have bigger masks. You can have a mask that are 5 and 5 into 5. There are 5 rows and 5 columns. There, it is not necessary that only rectangular or square masks be used. You know, there are even circular masks. There are even vectors, single column masks. But the most commonly used masks are square masks or rectangular masks, and all the masks in a square or rectangular mask have odd number of columns and rows because you want one left out. You know, one you need one to be a central pixel. So that pixel decides. So that central pixel of the mask decides which pixel of the image is being manipulated. If you're going to manipulate the first pixel, we make sure that the center of this mask is on that first pixel. So why do we have an odd number of rows and columns in a mask? So that we have a central pixel left out, you know, because if you're going to have even numbers, then there are no pixels left out. So we want a central pixel to be there in order to identify which pixel we're operating on. So that is the reason we have a odd number of rows and columns in each mask. So this is the most simplest mask you can see, 3 by 3 column, 3 into 3. You've got larger mask, 5 into 5. Now, before we step into the spatial filtering, now we've got this fundamentals of what is spatial filtering. Again, we're still in enhancement. We finished all the contrast enhancement, everything to do with intensities. Now, point processing, basically. Now in neighborhood processing. So all neighborhood processing means in order to define one point, we need a neighborhood. Now that neighborhood is defined by a filter. It's called mask. It's also called a kernel. Now this process of taking the mask, which has certain values known as coefficients, and merging it with the image pixels and producing a new image, that is called convolution or spatial convolution. Now what are the different types? Now like in all other subjects and like in all other theory subjects that I keep teaching and every other lecturer keeps teaching, we say whenever we come to certain topic called classification, you know, so whenever you make classifications, it is based on the way you look at it, you know. Like if you say please classify students based on trade, then we have DCST, DEHM, or whatever, DCIE. But if I say please classify students based on religion, then you've got Hindu, Buddhism. I could even say please classify students based on which football club they like. So classification depends upon the way you're looking at it. So even when we talk about classification, what are the different types of spatial filters? Depends on how we look at it. So the most commonly looked at angle for the different taxonomies of this types of spatial filtering is, one is what is the relationship, what is the operator, what kind of operator is being used, how are you combining these two, the mask, how are you combining the mask and the image. So you've got this mask. So depending upon this mask, so this is a mask and this is an image. So first, what are the different types of spatial filters? So first depends upon how are you combining these two images to get an output image. How are you overlapping this mask, and what are you doing with the weights, these coefficients of the mask, and what are you doing with the values of this pixel in order to generate an output image G of XY. So based on that operation, you can classify filters in different kinds. Now another way of looking at the classification of different types of spatial filter is when these two are combined, you get a certain output image. Now looking at the type of the output image, you know, what kind of output has this convolution generated? So looking at the output, you can have another classification of different types of spatial filters. So based on the operator, how are you combining the mask with the image? You've got linear. So when you're combining the mask with the image, if it has a linear relationship, linear is always, if you plot a graph, it will always be almost almost a straight line. For example, sum of product. So when you take sum of product, in any equation, that would always tend to be a linear relation. So any operation, when you're combining a mask and an image, if the operation that you're applying is linear, then all those methods come under linear spatial filtering. So there are average mean, weighted average, unsharp, derivatives. So these are all different types of filters we'll see. Now these are classified under linear because the operations used to combine the mask with the image are all linear in nature. Obviously, if there's a linear, then there's going to be a non-linear. So non-linears are filters that are also called order static filters because they depend upon certain order. Okay, so like the median. So in statistics, we know what a median is, or the central point of any data set. So we need to order the data set first, and then we find the central point. So that is why the other name is order static filters. Then there is another filter like max mean, where you really don't need a linear. It doesn't need to have this sum of product or weighted average kind of relationship, that you can term it as linear relationship. Then once you combine the image and you perform the operations on the mask and the image and the neighborhood and the predefined relationships, once you look at the output, so based on the output, again you can have two families of filters. One is called smoothening, or also low pass filters. The other is called sharpening, also high pass filters. So I've written this high pass filters twice, so you don't need to write this twice. You can make the change in your notes. So a smoothening or low pass filters. Now these two, smoothening and sharpening filters, are types of filters based on the output of the image. So when you look at an image, and if it is smoothened image, smoothened means blurred image. So if you've got an image and you apply certain filters, and then the output of the image is going to be a little blurred, and it's going to be blurred in a sense, it's soothing to the eye. So in some way it must have been really sharp image, and you've managed to smoothen it out, blur it out. So those methods are called smoothening or low pass filters. And if there is a very blurred image and then you manage to really sharpen it out, all the edges are very prominent, then we term it as sharpening or high pass filters. Now this low pass filters and high pass filters, again, they have their roots in signal processing. Like I said, convolution and signal processing. Low pass filters are generally done through averaging methods, and so we'll see all of this later on. But before we begin, there is another small fundamental issue that I need to discuss. Is there is a term called spatial resolution. Spatial means something to do with coordinates, something to do with the location. So spatial resolution means when you take a unit area, and in that unit area, how much difference, or how different are all the values. That is known as spatial resolution. So if I say a certain image has low spatial resolution, which means when you look at an image, most of the values in the image are constant. So for example, if you click a blackboard, and so blackboard is black, so the image values will almost be constant. So there is not much change. So even if you take a unit area and you see all the values within that area will all be almost near to constant. There is not much change. So though such images are called low spatial frequencies. Okay, so such images have low spatial frequencies. Now on the other hand, if you're going to click a very an image that has lots of objects and lots of colors, and lots of different objects and lots of different colors, bright colors, then you look at the values of that pixel, they're going to be a lot of changes. So if you take one unit area, that unit area is going to have a lot of changes within the pixels. So such images are called high spatial frequency. So such images have high spatial frequency. So there is images that have low spatial frequency. There are images that have high spatial frequencies. Images that have low spatial frequencies, we can assume it is the same object. So if you're clicking a blackboard and all the values are the same, so we can assume it is the same object. But if an image has very high spatial frequency, then we know there are a lot of edges in that image. So low pass filters are special type of filters that take high spatial frequency and convert it into low spatial frequency. And on the other hand, sharpening or high pass filters are such filters that take images with low spatial frequency like the blackboard and convert it into high spatial frequency. So probably it will try and detect all the edges of the blackboard and give you. So in a way, sharpening will the output of a sharpening filter or high pass filter will have all the edges highlighted. The output of a smoothing or a low pass filter will have all the edges blurred. And when you blur it, when you smoothen it, the main reason why you need to smoothen is you will tend to overshadow, or you will tend to delete all the small errors in that image. Okay, so so then what is the use of low pass filtering? Low pass filtering is to get rid of noises, small noises. Such small noises are called salt and pepper noises. You can Google that up, or we'll see it in the next slide. And sharpening filters are unsharp and Laplacian, and there are many others. So here is a tree taxonomy of the spatial filtering that we just talked about. So spatial filtering can be linear filters based on the operation between the mask and the coefficient. How are they being convolved? How are they being convoluted? And then linear, non-linear filters. Then based on the output. So a linear filter can have smoothing effect. Even non-linear can have smoothing effect. So based on the output also, you can define filters as smoothing or sharpening filters, or based on the predefined relationship between the mask and the image, you can have it as linear and non-linear. So that is what the different types of spatial filters are. Now in the next section, I've written some notes for you. This is basically to do with the different sizes of the mask. So I've already talked to you about this. Is like, it's not necessary that, so the masks also called as kernels or filters. Now it is not necessary that a mask always be square. It can be, kind of circular in nature, or it can even be, this is four nearest cross, or it can also be a single vector. But the most commonly used ones are these rectangular ones. Like I said, all of them would normally be in will normally have odd number of rows and columns. Why? So that a center pixel is left out, which identifies which pixel we are operating on. So it has odd numbers because we need one central pixel to identify the focal pixel, the pixel that is being manipulated on the image. So this is a mask. These are different types of convolution masks we can use. Now let us see the first kind, linear and non-linear convolution. So what is linear convolution? So like I said, whenever the relationship between a mask and the image, whenever the coefficients of the mask w of xy and the image f of xy are, whenever they're linearly convoluted to get an output image g of xy, such spatial filtering is called linear spatial filtering. What I mean by that is, let R be the response. So whenever you move a filter over an image, that filter is always going to have a response. Now if that response of that filter for that particular pixel is sum of products, is a linear product, sum of products, so weight of the kernel into value of the pixel. So the coefficient, the filter ko जुन चाहिँ coefficients are, filter ko जुन चाहिँ weights are assigned, in which location, -1 the location, if you multiply it with the image ko value at which location, again -1 at the same location, if you multiply it plus weight of second location, उसको corresponding image को location गर्दै तपाईले सबै add गर्यो भने एउटा filter को response आउँछ. That response, the output, that response of this filter is the output for which pixel? Is the output for the central pixel, f of xy. For example, we come back to this image. I think this is a very perfect image here. So for example, I'm calculating this. So say I'm going to calculate pixel by pixel गर्दै मैले सबै input pixel calculate गरेँ, म यो pixel मा आएँ, अब यो pixel calculate गर्न छ. त यो image ठुलो छ, धेरै ठुलो छ, त mask मेरो यत्रो मात्रै छ, calculation लाई यत्रो मात्रै चाहियो. So your mask will come and overlap this image here. Now I'm going to calculate the central pixel, the value of this is f of xy. I'm going to turn this f of xy into g of xy. So कसरी गर्छ रे, यो value j छ into यो value plus यो value j छ into यो value j छ. So the corresponding pixel location, mask location, the corresponding mask coefficient with the corresponding input pixel location, that is linearly added. Here in our case, sum of product. So when they are linearly added, and you suppose u plus u plus u into u plus u into you do multiply sum of product for all of this, and suddenly there is a response, there's a value. That value is the enhanced or convoluted value for this pixel. So f of xy will change. So that is why we've got this. Equation, here you go. So you can see the response for that particular instance is weight into that pixel frequency plus weight into next pixel frequency, likewise and so forth. Then you get a response. So this can be written as an expression where the filter size image, so the image size is capital M, capital N, the filter mask size is small m, small n. Now you can see you've got double summation. Why double summation? Because why? Because we've got to have the sum of all the weights and sum of all the frequencies. So there are many W's and there are many F's. So there are two coordinates here. So think of it as two loops, I and j. You know, so your first one -1 like constant Drachnus, you know, then your value change -1, then next one -1 remains, it becomes 0, then -1 remains, it becomes 1, then so I and j, so inner loop, outer loop kind of a thing. So g of xy, the expression is the output g of xy, this is the output image, is represented by summation of s equals to -a to a, t equals to -b to b, w of st, f of x plus s, y of t. So how do you understand this equation? You can just plug in a few values. Say a is 1, so from -1 to 1 we're going from a is -1 to 1 and b is -1 to 1. Okay, so -1 to 1, -1 to 1. So obviously if you come back to the image, it's pretty clear what I mean by saying -1 to 1. So if you look here, हामीले सबै क्याल्कुलेट गर्दा यहाँ फर्स्ट यो पिक्सलको क्याल्कुलेट गर्दा यसको माथि लेफ्ट अप्पर कर्नरमा के छ, -1 -1 छ, and when you come here it becomes +1 +1. So how much is it varying? The x coordinate is varying from -1, then 0, then +1. Y coordinate is varying from -1, 0, +1. So there is -1 देखि लिएर +1 सम्म, -1 देखि लिएर +1 सम्म. So that is the two coordinates we've got, locations. So in this equation again, so this is what, -1 to 1, -1 to 1. So you change bhaibhasta ta tyo pixel location पनि change bhaibhasta. So we're going to sum this up. This is called summation. So we're going to add. So first one we're going to take when a is -1 and b is -1. So the weight of -1 त्यो add -1 location ma त्यो coefficient, the kernel ko coefficient के छ त्यो into त्यो input image को x -1 and y -1. So first -1 हुन्छ. So the input image को -1 location into weight को -1 location. Summation भनेको plus, then this increases, this remains the same, this increases, -1 becomes 0. So then weight of -1, 0 location into frequency input image of x -1, y 0 or y. Then again -1 remains the same, this becomes 1. So weight of -1, 1, that location, and input frequency -1, 1. So this keeps adding up, and then you finally get this. So if you simplify this, and you get this equation. So this is how a linear spatial filtering works. Okay, so here are a few points. The coefficients W00 coincide with the image value f of x and y. This is what we've already said. Now the input size, the mask size should always be odd so that we have a central pixel. Now this is the assumption. So m is always going to be this, and n is always going to be this. Why? What is m and n? M and n is the size of the kernel. Capital M and capital N is the size of the input pixel, input image. Small m and small n is the size of the filter that we're talking about. So this is always calculated using this formula. You can use it. Why? Because to make this m and n always odd. So for example, let's just take a is 1 and b is 1. So if a is 1, 2 into 1 is 1 plus 1 is 3. and B is also 1. So 2 into 1 is 1 plus 1 is 3. So M is 3, N is 3 for all values of A is 1 and B is 1. If you take A is 2, B is 2, this becomes 5, 5. So the filter size keeps increasing, 3 into 3, 5 into 5, 7 into 7. Why? This is the reason why. Because M is always equal to 2A plus B and N is always equal to 2B plus 1, where A and B are always non-negative integers. Now let us understand this entire linear spatial filtering through an example. I think this will be very easy to understand with an example. So let's say this is an image. This image is of size 5 into 5. There's 5 columns and 5 rows, and this mask is of 3 into 3. Fine. Now we are calculating this part of the pixel, this picture. We'll be calculating, we'll be transforming the whole picture, but we are just considering that. Let's for example say that we are enhancing this shaded portion of the image. So at the first instance, we need to keep the central pixel W00 with the pixel that we are going to modify. So the first pixel we want to modify is 50. So obviously this 1 by 3, this is the central pixel of this is the central coefficient of the mask. This must coincide with 50. So this mask will come here, and obviously this area 1, 2, 3, 50 go 1 to 50, your area, all this area. So we'll have this areas. Yeah. So the filter will come and place itself, overlay itself on this area where the central pixel 50 coinciding with half here. So then how do you calculate it in a linear spatial filtering? Is a sum of product. So take 0 into 30 plus 1 by 6 into 40. So 0 into 30 plus 1 by 6 into 40. I've done this for you. Then 0 into 50 plus half into 40 plus 1 by 3 into 50 plus 1 by 6 into 80 plus 0 into 35 plus 1 by 6 into 255 plus 0 by 70. You get a certain response of that filter after you do all this predefined relationship. The response is 85. Now this 85 is what? The response belongs to which pixel? This 85 belongs to this filter calculation garera, convolution garera. The response of this filter became 85 when the central pixel, this W00, was on top of this pixel XY, that is 50. So the response of this filter was 85. Now this 85 belongs to this pixel. So now the 50, after this image undergoes linear spatial filtering, then when the value of that pixel was 50, after the spatial filtering, linear spatial filtering, the value of this pixel becomes 85. So likewise and so forth, you can start counting for, we can take this linear filter and then move one to the right. When you move one to the right, then it will have an image defined like this, because this whole filter will come on top of this, keeping this central pixel 1 by 3 on top of 1 by 80. Now the response of the filter is calculated again. How is it calculated again? So 0 into 40 plus 1 by 6 into 50 plus 0 into 70 plus 1 by 6 into 50. So it's a sum of product. We need a sum of product of all the thing based on the equation we've seen earlier. Then the response at this pixel will also come out. The response of the filter for this particular location. So after filtering, this value 50 becomes 85, 80 becomes 65, and 60 becomes 61, and so on and so forth. You calculate for 25, 70, keeping in mind when 25 is the pixel under consideration, or when 25 is the focal pixel. That's what we say. So when 25 to 55, that pixel location is the focal location, focal pixel. Then when you put this mask on top of this, the mask will overlay itself like this, so 255 will be the central pixel, and then this mask, and then you can calculate the calculation again. So after you do all the calculations, the image will look something like this. So this was we do filtering for the whole image, but for for understanding purpose, we're only going to do filtering for this image here. With this mask, given mask, 3 by 3 mask, we're going to convolve this. How is it going to do? What kind of spatial filtering are we applying? We're applying a linear spatial filtering method where there's going to be a sum of product between these two, where the mask moves pixel by pixel, and based on the response of the pixel, the central pixel value is changed. So when you do that, these values get changed to these. Okay, so I have done 3 for you. I hope you will do it and complete the rest in your notes. So that's how spatial filtering works. Now the same spatial filtering, this entire mechanism that we talked about, this summing of the weight with the frequency, again summing of the weight with the frequency, every time changing the location of A and B. So this is when we consider x and y, so this is a two-dimensional figure. But if you were to vectorize it, vector means it has only kind of one dimension, so single column or single row. So if we consider it that way, even more simplified equation would be this. So the response of the filter is always equal to weight 1 with the image value z1, weight 1 into the image code z1, exactly wherever it is coinciding, and weight 2 into image goes z2, or likewise and so forth with w3 z3. So this can be summarized as single summation I tends to 1 to 9 wi into zi. So here both of them are having an I suffixes. They are not having x and y or I and j. So that is why we also call this as a vector representation of the linear filtering. So please remember this equation, remember the above equation. How did this equation, how were you able to form this equation? Because we had this relationship here, the response was calculated like this, and if you were to take this entire calculation and convert it as a generalized equation, this is the way linear spatial filtering generalized equation is. And you can also write this general equation as a vector representation of the same equation as this. Okay, and you'll also remember the sum that we've done for your exam purposes. Then next we come to spatial low pass filtering. Okay. So what are low pass filtering? We've already said low pass filterings are those filtering methods that okay. Just need to view. I don't know if it's working actually. Okay. So then we come to what are low pass filters. Now low pass filters are also called as smoothening filters because they're also linear. So linear means they will always have this linear operations kind of sum of product kind of relationship that we've seen above. But why is it called low pass? Because like I said, spatial frequency means per unit area how much changes in the intensity values. So if there are a lot of changes, that means there are a lot of edges. If there is no changes, we know it is a constant background image. So low pass filters will generally block the high spatial frequencies, and in doing so the resultant image g of xy is a blurred image. So it is also called as smoothening or a blurring filter. Why is it used? It is normally used to remove noises from the image and to have some pleasing kind of an image. Sometimes the images you've seen olden days black and white TV, they have lots of black dots. So these dots are called salt and pepper noise. Whenever sometimes you do Xerox, and when you Xerox a paper, or when you scan a paper, some kind of noise appears in the image as fine dots all over the image. Those are called salt and pepper noises. So in order to remove these salt and pepper noises, normally blurring and smoothing filters are used. So what are the different blurring and smoothing filters? So one is called the averaging filter. So averaging filter is also called a mean filter. It is also called a low pass. It is a type of low pass filter. So averaging filter is also called mean filter, fill in the blanks, and it is a type of low pass filter, and it is also a linear filter. So the averaging filter has a mask of 3 by 3 generally. And this is the simplest averaging filter, has a mask of 3 by 3, kernel of 3 by 3. It is also called kernel, and the values or coefficients of that mask is all 1. And so what does this say is that, what is it saying is that the weights of each pixel position of the mask has an equal effect on the filtering process. Okay, they contribute the same weight, so all of them contribute the same weight, and ultimately we are kind of dividing it by 9, bringing out an average, so then the image scale remains the same. If it was from 0 to 255, it should still remain 0 to 255 after applying the linear operation on the image. So this is the spatial filtering. Spatial filtering low pass filter. Okay, linear spatial filtering low pass filter को first example. Linear spatial filtering को low pass filter को first example is average filtering. The name of this is average filtering, or it's also called as mean filters, because you're finding the mean. Average means average of 10 numbers is you add up all the 10 numbers and divide by 10. So that's an average. Then, so how does this work and why does it work? Now there is a very small example here. Supposing this is an image, and somewhere you've got this noise embedded in this image, and this noise is represented by this 5 and 0. Now when you apply this averaging filter, then this noise somehow becomes, this filter gets an average value of its neighborhood. So somehow this noise, or an outlier, can be removed to some extent. So once you apply this averaging low pass filter, then this image gets denoised, and you can see this is second column, second row, second column, second. So this gets an average value of 182. This is 5, 182, and this becomes 183. So somewhere the noise has been removed by applying the average filter. Now a different form of average filter is called weighted average linear filters. So average filter के extension है आर जिसका नाम से weighted average linear filters. Now if the filter mask has some weights given to the 4 neighbors, you can see we've talked about 4 neighbors and 8 neighbors in class. So how do you transverse a pixel as 4 neighbors or 8 neighbors? So pixel connectivity, I think it's under pixel connectivity. So the 4 neighbors have certain weights, and when you give this particular weights the 4 neighbors, this becomes an average filter, but a special kind of average filter called a weighted average filter. And here it is divided by 16 because the total value is 16. Again we said divide by 16 because so that the image stays within the same scale. You don't want the scale of an image you don't want the scale of an image g of xy to become different from that scale of an image f of xy. So input image scale must be same as the output image scale. So that is one reason. So we've seen the first 2 kinds of filters. What kind of filters? Low pass filters that are linear in nature, and whenever these filters work, the output of the filters has a smoothing or a blurring effect. So one is called an average filter, where all the coefficients of the filter are 1 1 1 1, and you've got you've got 1 by 9 also as a coefficient here. And a weighted averaging filter where the 4 neighbors have certain weights, then the other corner diagonal neighbors ND4s, and you've divided by 1 by 16. Now for example, let us take this image. Now all these are, remember, these are spatial filtering methods. So we've already seen the equation for spatial filtering is a sum of product. So if this is the image, and if you were to apply this filters on top of this image, so it's the standard filter, if you apply the averaging filter, and this is the equation it's gonna take. So if the filter is placed here, okay, and so 110 into 1 plus 120 into 1, so 110 into 1 is 110, 120 into 1 is 120, 90 into 1 is 90, then 91 into 1 is 91, 94 is 94, 98 is 98, then so this three parts, you know, this mask is going to overlap here, is going to define the neighborhood of this. So the response of this filter on this image here, after you divide it by 9, so you're going to divide it by 9 because this coefficient is also here. So after you divide it by 9, the response of this filter at this location is 98.1. So this response belongs to the value 94. So 94 gets changed to 98.1 when you apply the averaging filter. Now if you were to apply the weighted averaging filter, same thing, 1 into what's happening, 110 into 2. Okay, so it's shifted. So once you shifted a little one to the right, then you are having 110 into 2. Sorry, it's the same location, it's the same place. So 1 into 110 is 110, fine. Then 120 into 2, 120 into 2 plus 90 into 1 is 90. Then 91 into 2 is 91 into 2 plus 94, this value into 4, because your tinta row tinta column यहाँ आएर बस्छ नि tinta row tinta column. So equivalent pixels are being mapped, and finally you're dividing by 16, and then for this pixel 94 becomes 97.81 when you use weighted averaging filter, and 94.94 becomes 98.1 when you use averaging filter. So यो एउटा pixel मात्र गर्दैन, डल्लै image मा गर्छ, but we are just showing you, at least I'm showing you only one pixel how it is done. Now this is a nice application of this averaging filter. So you can see this, it's not very clearly shown, but this image is taken from a Hubble Space Telescope. So there is a satellite, and then in the satellite, in the space station, there is this Hubble telescope, and Hubble telescope, no, not in the satellite, I think the Hubble telescope or whatever. Okay, so this telescope को image हो यो, तो यो image में you can see a lot of blurry salt and pepper noises are there. So these small things don't contain information, they only contain noise. So you apply a low pass filter or an averaging filter or weighted average filter or some other low pass filters that will blur the image or smoothen the image. So which means we're going to apply some kind of smoothing or blurring filter. And after that, we've already learned in our first spatial enhancement video and tutorial about image threshold. So there is a certain point, threshold is a certain number. Below that number, everything becomes white. Above that number, everything becomes black. So if we have only the white parts to be white and all the black parts to be completely black, and all the middle range, all these middle values will either become black or either become white. So if this small value here, this particular value is somewhat gray, so 50%, if we keep the threshold 50%, so all 50% like muni black becomes black, all 50% white becomes white. So light shades of gray will all become black. So all these becomes black, and kata white will all become fully white. So suddenly the image becomes very crisp, and now they can do all the studies that they want, and the image is very pleasing to the eye compared to the first one. So just the blurring filter will not serve the purpose. We've also done a thresholding operation on this image. So thresholding is again point operation. Blurring is again a neighborhood operation. So this is spatial filtering, and this is contrast intensity enhancement. We've done in the previous class. So then we come to the smoothening filters. Like I said, smoothening filters will try and smoothing filter ले के गर्छ, smoothing filter ले high pass filter ले के गर्छ भने just the opposite of low pass filter. Smoothing filter ले जति पनि edges छ images को, sharp edges, like for example if you're looking at me, my head and my background, my head has certain edge, certain boundary, so all these edges are going to be highlighted, all these edges are going to be enhanced, and all the other images, the background images, all the colors that are constant, So all my face color, all these are constant, but the edge, my head ko edge with the background, this is an edge. So all these are constant, you know. So if you were to calculate the values of this pixel here, this will probably have a low spatial frequency, but my head ko your border with the background, this area is going to have high spatial frequency. So high pass filters are going to enhance this high spatial frequency and they're going to suppress this low spatial frequencies. So border चाहिँ यसले enhance गर्छ सबै edges images को. Fine. So there are the following types. Okay, so there are many kinds of high pass filtering filters. We are going to talk about just one for now. It's called unsharp filtering and high boost filtering. Now unsharp filtering and high boost filtering is almost the same thing. The high boost filtering is an extension of the unsharp filtering. Now why is it called unsharp filtering? Because we're going to take the unsharp image. Unsharp भनेको blurred image. So first we're going to have an image. And say for this is the image, and we're going from that image we're going to take out a blurred image. So how do you take out a blurred image of this image? We can apply low pass filters like average filters and weighted average filters. So you do some kind of filtering, low pass filtering in this original image, you get a blurred image. Okay, now you take this blurred image and you subtract it from the original image. That is called unsharp filtering. So first, so the equation of unsharp filtering is something like this. The output g of xy is represented by this is the original image. So original image बाट के minus गर्दैछ त्यही image को blurred version. So f of xy को blurred version. So f of xy को blurred version कसरी निकाल्छ? f smooth is represented as blurred version, a low pass filtered version. So you कसरी निकाल्छ? By applying low pass filter to the image. So when you apply a low pass filter to the image, you get certain one image. That image is called f smooth. If you apply average filter to an image, the output is called your f smooth image. Now if you take that f smooth image and minus it from the original image, you get another image. Now this is called your unsharp filter. You have used an unsharp image, a blurred image. You've minused it from the original image to get an output image. Now this is called your unsharp filter. So what is this doing? It will detect all the edges, you know, to an extent. The edges won't be really beautiful to look at, but somehow it will suppress all of. So even if you imagine you have an image f of xy and jati pani blurred version of the image. Blurred means continuous images. So like my skin tone is continuous. So this सबैलाई suppress गरिदिन्छ. Continuous tone लाई चाहिँ image बाट निकाल्दैछ. The continuous tone निकाल्दियो image मा के उब्रियो? Only the edges. So if there is an edge, there's an image, is some kind of an image, and from that image you take away all the continuous low frequencies. Same values लाई चाहिँ suppress गर्यो भनेपछि what are you left with? Same values suppress गरे image भनेपछि only edges are left. So this is an edge image. You have one edge image. So this is symbolically represented where the original image, if you smoothen it, low pass filter, you get certain output. Now the output ला तपाईले original image देखि minus गर्यो भने you will get an unsharp filtered image which detects edges. Now यो image मा सबै edge मात्रै छ. अब यही image मा यो जुन चाहिँ image आएको छ तपाईको g of xy, यो g of xy यो sharp image हो, edge, an image that has edges. Okay, now यो image जुन चाहिँ edges मात्रै छ अनि अरु चीजहरु चाहिँ अलिक सप्रेस भएको छ, edges चाहिँ धेरै छ. त्यो edges धेरै भएको image लाई गएर फेरि original image सित add गर्यो भने, so there is an image, this is the image, and यही image को एउटा edge image छ. Only the edges are there. So this is an original image, this is an edge image. So यो edge image which is the g of xy here. So edge image लाई तपाईले गएर यो original image मा add गर्यो भने it will further enhance the edges. किनकि यो original image मा edges त छँदै छ हैन, अनि अरु constant area पनि छँदै छ, यो white all this constant area, but this becomes an edge because this has some other there is compared to my background, there's an edge here. Here there are edges. So यो original image मा तपाईले यही image को अर्को एउटा image छ g of xy जुन चाहिँ मात्र खाली यो image को edge मात्रै छ, यो image को यो माथि बाहिरको edge मात्रै छ values. यो edge values, if you go and add it to the original image, this images further gets enhanced. So that is called your high boost filtering. So you're boosting that filter, so you're sharpening the edges. So the equation takes the shape of this. So high boost filter f sharp is, if you have the original image and in that original image if you add g of xy, this g of xy is what? The unsharp filtered image, this g of xy, the unsharp filtered image. So g of xy, like तपाईले f of xy मा हाले पनि it becomes sharp. Now the k is a constant, so कति degree सम्म तपाईले त्यो edge लाई sharp गर्ने. यो k is kind of a TV मा पहिलाको TV मा त यसो घुमाउँथे नि हैन, त्यो contrast मिलाउने, brightness मिलाउने. So the k is something like that, a knob. So you can keep increasing the k constant. So तपाईको image को edges sharp हुन्छ, तपाईले त्यो k लाई बढाउँदै गयो भने अझै sharp हुँदै जान्छ edges. So k is kind of a scaling constant. It scales the entire effect of this unsharp image. So yeah. Okay, so this is wrong. This is wrong. Spatial high pass filtering when smoothing लेखेछु. High pass filter means not smoothing, but please correct this in your notes. Okay. So high pass filtering means not smoothing. Smoothing means low pass filtering. So high pass filtering means sharpening. Okay, so I'll also save this. So it's called sharpening. Fine. And then you don't have to look at this image. I think we can do without this. Fine. Now look at this example I've got. Okay, so this is an original image. So in the original image you've got two edges. You've got edges here and you've got edges here. Now when you apply a low pass filter, this image becomes blurred, so the edges vanishes and it preserves the low spatial frequency part of an image, and it blocks the high spatial frequency. High spatial frequency में जहाँ changes धेरै छ, so changes धेरै यहाँ थियो, यहाँबाट change गर्यो, यहाँ change गर्यो. Now when you apply when you minus this blurred image from the original image, you get an unsharp mask. This is called unsharp mask, g of xy. Again, so g of xy ma, it has only detected the edges. You can see edges यहाँ रहेछ, यो image को edges यहाँ रहेछ. All other parts of that image have been filtered off. अनि अब फेरि हामीले यो edge image unsharp mask लाई गएर original image मा add गर्यो भने यो image मा, so यो unsharp mask which has only the edges here clearly defined, maybe not very enhanced, but edges are there. So these edge information image, if or unsharp mask image, if you take this and add it to the original image, it will further boost this edges. So then the sharpened image or the sharpened edge will be this way. So you've got the original image back, but with very high highlighted edges. So you know exactly where the boundaries are and you can differentiate the different objects. Let's take for example this. You've got an image and you blur it up, and you take the blurred image and you minus it from the original image. You've got the edges, and when you've got these edges, if you go and add it to the original image, the edges become even more sharper, but depends upon the value k that we talked about. If the k is high, the sharpening becomes even more high, this k. So if k is 1, nothing much. If k is 1, it is called unsharp masking. So in this equation, high boost filtering equation, if k is 1, it is called unsharp masking, no effect. But if k is if you keep increasing k 1, 2, 3, 4, then the effect of this high boost filter will be more. And so as and when you increase your k, so image filtering गर्दैछ तपाईले गर्दैछ, कोड लेख्दैछ, k लाई तपाईले चेन्ज गर्दै 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 आउटपुट हेर्दै गयो भने the images get further and further enhanced, so to an extent where after a certain threshold the image doesn't look very pleasing. So let's just see here. This is the original image here. Okay, and then we do blurring from this low pass filtered image, and after we do the low pass filtered image, we minus it from the original. So all this blurring is minused, only the edges remain, and this edges, like if you add it to the original image with a certain scaling factor k, you get an image that has a very nice edge. Sharpened image, that's what we say. So there are other kinds of, then the last kind of filtering we'll see is a non-linear filter. Okay, so non-linear filters are also called order static filters. So these are non-linear because of the fact that they don't have the sum of product kind of an equation. So the first of its kind is a median filter. So median filter is again, you find the median of all the numbers. So if, for example, or how do you find medians? If so how do you find median? So say for example, you've got तपाईँहरूको क्लासमा जति पनि नानीहरूले मार्क्स पायो सबैलाई एसेन्डिङ अर्डरमा राख्यो. सबै नानीहरूले जति मार्क्स पाएको छ, से इमेज प्रोसेसिङ टेस्टमा जति मार्क्स पाएको छ 20, 50, 60 whatever, so all those marks you keep it in ascending order, you count equal number of people from both sides, and when you come to a central point, that is the median. If you don't have a central point, you दुईटा पोइन्टको बिचमा छ भने त्यो दुईटा पोइन्टको बिचको भ्याल्यु हुन्छ. So finding a median, so there is no sum of product as such. And so one thing I forgot to tell you is low pass filtering all the filters were made by averaging. So averaging in a sense tends to integration, discrete integration. High pass filtering, mostly all of those filters equations are derived from partial differentiation. Okay, so low pass filtering ma definite integral चलाएर गर्छ अनि high pass filter मा partial derivative निकालेर गर्छ. Non-linear filters ma it's only statistical measures that we take. For instance, median is a statistical measure. Then for example, here consider this image 5 into 5. Now we're talking about this image, So this is an image, fine, and we're going to have a mask of 3 by 3 mask, and we're going to apply a median non-linear filtering or median filter. So median filter ma ke huncha bhane अब यो मास्क चाहिँ यो भ्याल्युको लागि दिस इज द फोकल पोइन्ट 255 यो डल्लै मास्क हो. मास्कमा हाम्रो कोएफिसिएन्ट्स छैन. अस्तिको त्यो लिनियर स्पेशल फिल्टरिङ जस्तो इभन द मास्क ह्याड भ्याल्युज. नाउ दिस मास्क डजन्ट ह्याभ भ्याल्यु. दिस मास्क आर ओन्ली डिफाइनिङ द नेबरहुड. यति ठुलो नेबरहुड भनेर यो मास्कमा एज सच वेट्स छैन, कोएफिसिएन्ट्स छैन. र यो डल्लै मास्कमा जति पनि पिक्सल्स छ इमेजको, अल अफ देम यु राइट इट डाउन इन अ एसेन्डिङ अर्डर. देन यु फाइन्ड द सेन्ट्रल पिक्सल which is 30. Okay, similarly here you find all these values, you write down in ascending order, and you find the central pixel is 0 0 यहाँ छ, 20 20 यहाँ सबै पिक्सल लेख्यो, अनि 1 2 3 4 1 2 3 4 80 is the middle pixel. You have to sort this. यो सबै भ्याल्युजमा मिडल पिक्सल कुन चाहिँ छ? 80 छ. सो यो 70 को ठाउँमा 80 आउँछ. Now you again shift the mask one to the left. When the mask shifts again one to the left, you write down all this pixel. You're trying to find the median of these values. So you write down all these values in an ascending order, and whatever is the central pixel in this ascending order, you say यो height wise बसी अरे, अनि height wise बस्दा बिचको मान्छेको छ यो 100. So यो 0 को ठाउँमा 100 जान्छ. So likewise you would have done for all the pixels. Okay, median filter ले त्यसो गर्छ. त त्यो चेन्ज गर्दा फिल्टर्ड इमेज यस्तो हुँदो रहेछ. Yeah, something happened. Okay, filtered image becomes 30, 80 and 100 if you use median filter. So 30, 80 and 100. So this 255, 70, 0 becomes 30, 80 and 100 because of the median filter. The median filter ले पनि smoothing effect दिन्छ. It's also a type of blurring filter. तर average filter भन्दा less blurring हुन्छ हैन. त कसरी भन्दा you can see an image here. So this is the original image. Okay. So यो image मा यस्तो धेरै हुन्छ पुरानो किताबमा है. So on the left hand side you've got an original image. Okay, you've got an original image on the left hand side. Okay, so you can see a lot of salt and pepper noise. This is not information, this is noise. You know? So noise can be because of some sensor fault, some printer fault, some pixel fault. So all of these noises are removed by some kind of blurring or smoothing filter. We know one kind of smoothing filter is averaging filter. The other kind of smoothing filter, low pass filter, is called weighted average or averaging filter. So when you apply a low pass filter, a blurring filter, a smoothing filter, this is what happens. Most of the salt and pepper noises have been removed. Now another kind of blurring or smoothing filter like the averaging filter is the median filter, which is non-linear. These are linear. So linear smoothing filter le yesto gardo रहेछ. Linear smoothing filter. The smoothing filter yesto गर्दछ. So non-linear smoothing filter such as the median filter ले के गर्छ? This is the output. You can see. So blurring कम्ती भएछ यसमा. So दुईटाले नै noise त निकाल्यो. Averaging ले noise निकाल्यो salt and pepper अन्त median ले निकाल्यो. तर median मा blurring कम्ती भयो. So it is much better to look at. So this is a median filter. So another kind of non-linear filters besides the median, यो त median भयो हैन. यो median filter मा के गर्छ हामीले mask को भित्र जति पनि छ त्यसलाई sort गरेर लेख्छ अनि त्यसको बीचको value is replaced here. There are another kind of non-linear filters called min max filter. Min filter मा के हुन्छ भने सबै ascending order मा लेख्छ यो जति पनि mask को under मा values छ त्यसको जुन चाहिँ minimum value छ. So यो mask मा कति minimum छ 20. So 255 will be replaced by 20. So every time the mask moves, the minimum value of that mask will be replacing the focal pixel. अर्को खालको छ max. Max मा के हुन्छ भने the maximum value of the pixel will be replacing the focal pixel. So that becomes a min max non-linear pixel. So median pixel huncha, min max non-linear pixel huncha. And so that's it. So that's the end. Thank you so much. पहिलाको enhancement मा धेरै लामो भएर we had not done histogram processing. So that histogram equalization भन्ने एउटा method छ, that is something we've not done previously. So that is what we're going to do in the next time. And I'm also going to show you certain ways to enhance your image. Okay, for example, we're going to see in the next class how to install Anaconda for the Python environment, or there are other softwares like Canopy. So we're going to install one of them, and we're going to use the SKM image library, which we've already done in class. I've already shown you, but we'll do it in a little more detail, and we're going to see a few of the contrast stretching, a few of the histogram equalization. Histogram equalization baki chai, so that is still there. अस्तिको same webinar धेरै लामो भयो, मैले stop गर्दैछ, notes मा छ. Okay, so that's very important. Histogram equalization is very important. If you can study it on your own, please study it on your own. And then we're going to see how we're going to use the SK image scikit-learn को Python को scikit-learn image processing library को commands ले गर्दा how can we enhance images. We're going to see all that basics we've already seen. We're going to see, we talked about histograms, and we're going to see how to take out histograms. So I've just taken this histogram out for this image. This was the color image. We've already talked about this astronaut color image, and I converted the color image into gray. Gray has all values. I mapped it with the gray color, and I took out the histogram of this image, and then this is the histogram of the image. So you can see this is the very black parts of the image because it's 0, and then this image has a nice kind of a contrast because it's taking up the entire scale from 0 to 255. Now again, there could be a question, so why is there no 0 to 255? It's showing 0 to 1 because this is a normalized scale. And then if you find out, most of the images that you import through Python into the language, they come as a different format. So I try to print out one of the values. So for example, your image go 100 column 100 row मा 2D array हो, तो 100 column 100 row मा this numpy array हो, तो 100 column 100 row मा value के थियो भन्दा value यो रहेछ, grayscale value. The 0.60, so this image format is a floating point format. This is a floating point format, so we have to convert this into a integer format. 8-bit, so that it becomes 0 to 255. So the scaling kasari garcha, all of these things we will see. That scaling garepachi यो image को pixel size gray level values पनि 0 देखि 255 सम्म नै आउँछ. So histogram हामीले पहिला हेरिसक्यो. This is the frequency, the occurrence, कति occur हुँदैछ, and these are the frequencies. Okay, so till next class, please wait up, because the next class we're going to see a few hands-on